In 1995, the numbers being used by the navigation system of the Mars Climate Orbiter were correct, but the units were not. There was a miscommunication regarding English versus metric units. This led to the loss of the satellite, a cost of $125 million, and it slowed the progress of planetary science. In math, we often deal with pure numbers, 12, 10, but in science, most quantities have both a number and a unit, like 12 meters and 10 seconds. These units really matter. This is Real Chem. Proportional reasoning is more powerful than you can imagine. If you run twice as fast, you'll get there in half the time. Proportional reasoning harnesses our intuitions. When we couple proportional reasoning with the units of our values, we get dimensional analysis. And dimensional analysis makes applying proportional reasoning even easier. It's all about paying attention to the units attached to the numbers. Let's explore. Many equations and relationships in chemistry are proportional relationships. If I double the volume of coffee in a cup, the mass of the coffee also doubles. This implies mass is proportional to volume. To convert this proportionality to an equality, we introduce a proportionality constant. Mass is equal to a constant times the volume. Many of the properties that we work with in chemistry are proportionality constants. In this case, the constant is named the density of the substance. So mass is equal to density times volume. The units on the left and right-hand side have to agree. So density must have units of mass over volume. For instance, if we use grams for mass and milliliters for volume, density must have units of grams per milliliter. The milliliters cancel, and we have grams on both sides. This is where dimensional analysis comes in. We have a proportional relationship, and if we pay attention to units, we can easily solve computational problems like this one. What volume of sugar has a mass of 45 grams, given that the density of sugar is 1.6 grams per milliliter? We start with the given quantity, the grams of sugar, and then consider the units of our answer. We want volume, so we need to have milliliters at the end. We know there is a proportional relationship between mass and volume, and that includes density. So we use the density to get from our given to our target. In doing this, we must get the units to cancel correctly. So we must have milliliters on the top and grams on the bottom. The density is 1.6 grams per milliliter, so the 1.6 must go in the bottom. And we have our answer. 28 milliliters of sugar will give us a mass of 45 grams. This shows how the process works, but it doesn't really capture and show off the power of this method. Let's try something a bit more involved. Kerosene is often used to launch satellites into space. How many gallons of kerosene do we need to launch a rocket if it takes 3 billion joules of energy? We can search the web and find the density of kerosene. We also find that burning a gram of kerosene releases 43 kilojoules of energy. We can write this as a proportional relationship. We also have some unit conversions we'll need to get all the units to cancel out correctly. So our given here is that we need 3 billion joules of energy. Our target is the volume of kerosene in gallons. So we can use the energy from combustion to get from joules to grams of kerosene. The density gets us from grams to milliliters. We convert milliliters to liters. We convert liters to gallons. Well, we're done. See, it's all about following the units. We need 23,000 gallons. Whew, that is a lot of fuel, but it is a rocket launch we're talking about here. I hope you'll agree that dimensional analysis gave us a pretty intuitive way to figure out the amount of fuel we need for our rocket launch. When I send my number of 23,000 to the engineers, I'll be sure to attach the units and emphasize that it's 23,000 gallons, not liters. So, explore and remember to have fun.